the Simulation Industrial Chair. We would like to thank you for attending this webinar, in which we have two great presentations entitled The Attenuation of Seismic Waves, presented by Dr. Nicola Sato, and Fracture Detection in CT Scans, presented by a student of his, Mr. Omar Alamoudi. So first of all, we start every presentation by introducing ARMA. So ARMA was established in 1995 from the US National Committee of Rock Mechanics, with the mission to be a worldwide recognized representation of multidisciplinary rock mechanics advancement and application, with the aim to serve its members and the public. As of now, there is around 1,200 members that range anywhere between petroleum, civil, and mining industries. There is over 30% of these members are students, and they represent 14 active chapters right now, of which the University of Toronto is the newest established student chapter. So I would start off with introducing our team. So myself, Ali, I'm the president. Mayli, the vice president. Earl Maxibuk is the treasurer. Karima Bayana is the secretary. Rizawat Haley is the event coordinator. And we were newly joined by Ms. Firasu, who's the social media and outreach. The aim of the team is to provide networking opportunities with leading industry and academic professionals, in which we are in one today, by providing online and offline presentations. And we provide a place where students can share and collaborate, and they work through a series of open discussions, again, just like the one we have today. And always, this is an open call to share and exchange ideas and information between rock mechanics practitioners. We also invite you to follow our media channels. So we have a current website where we keep all our events up to date. And if you become a member, then you join our mailing list and you get updates of when is the coming talks. We also have a Twitter channel and a YouTube channel. So our YouTube channel is where you can find a recording of this video after we are done. And as a reminder, this presentation is being recorded. So first off, we would like to welcome Mr. Omar Alamoudi. Mr. Omar is a PhD student at the Rock Deformation Lab in the Jackson School of Geosciences at the University of Texas at Austin. His research is building and utilizing hydraulically activated X-ray transparent tri-axial testing apparatuses. With his research primary objective is to understand how fracturing of shale rocks affects their hydraulic permeability over time. Previously, he completed his master's at Stanford University in Geophysics, for which he worked in Saudi Aramco in Geophysics for 4 years, with his experience in seismic data acquisition, seismic data processing, interpretation, and geological modeling and rock physics feasibility studies. His title today, the title of the presentation today is Fracture Detection in CT Scans. And with this, I would like to hand it over to Mr. Omar to start his presentation.
Thank you very much, Ali, for a generous introduction. Hello, everyone. Here in Austin, it's still morning, so good morning. Do you see the correct screen, or do you see the presenter view?
It is the correct screen.
Okay. So today I will talk about fracture detection in CT scans, particularly of rock CT images. And the general outline of the talk is I'm going to motivate the topic, and I will have a brief introduction and then discuss the methods, the results, and discuss them further, and finally conclude. I encourage, if you have any questions, although I remember that the outline and the format is to hold off, but I actually don't mind answering questions if the other hosts allow it during the talk. So why do we care about fractures? Fractures are actually prevalent in many industries and in many applications, but since I come from an oil and gas background, some of the applications that are relevant to my work are in the drilling application, where loss of circulation is a huge problem that costs a lot of money, and preventing it or understanding when to anticipate it is of critical importance, as well as fracture design, where humans induce fractures to enhance the production of hydrocarbon fluids. Another problem that is of particular intrigue to me is the rapid decline in unconventional resources, or in the production of unconventional resources compared to conventional resources. We know that unconventional resources usually are produced from reservoirs such as shales with very tight permeability and very low porosities. However, this very rapid decline in the production is of a particular intrigue to me. Of course, fractures are not only exclusive to hydrocarbon reservoirs, they are also pertinent to hydrothermal reservoirs. And lately, another trendy topic is in understanding the cap rock integrity for CO2 sequestration as well as nuclear waste management. So understanding fractures and how they develop within rocks, particularly cap rock when it comes to a storage application, and a reservoir rock when it comes to a production application, has importance in all of these different industries, and it really does not matter what type of fluid that you're producing or trying to inject. And with that in mind, we would like to understand how fracturing rocks actually improve or reduce the permeability of these rocks. And to do that for my research, I intend to use a X-ray transparent tri-axial testing apparatus. This is a schematic showing that apparatus. Earlier, I was able to show the executive committee some other images. This apparatus has an axial piston that provides the axial pressure on a rock sample. This rock sample is also embedded in between two piezoelectric transducers that we use in measuring VP and VS velocities. And this entire apparatus is then embedded within a MicroCT scanner over time. So we take it, we subject the rock sample to specific conditions, pressure and force conditions, and then we take it inside of the scanner, take an image, remove it, and increase the forces, and then take another image, and so on and so forth over time. In addition to acquiring VP and VS velocities, we can also acquire permeability data using a transient pressure method, where a pulse of pressure is applied to the top of the sample and the pressure is monitored at the bottom of the sample as well. So here we can acquire basically, in addition, of course, to the strain and stress conventional curves. So we have 3 data sets, that's VP and VS velocities and permeability measurements, stress and strain curves, in addition to MicroCT images. And we'd like to integrate all of these to understand how permeability varies as we subject our rock sample to an axial force. Our apparatus also is designed to handle applying different strains and different strain rates on the rock sample. So a general question would be, in which stage of the deformation regime is permeability maximum? And this apparatus will help us understand that. To have a very general view of what MicroCT images of rocks look like, so this image shows 3 slices at different angles of a rock sample embedded in the middle, showing different shades of gray. The gray value usually is a very good proxy for mass density. And since we are interested in fractures, we know that fractures are low density regions, and they show very well in MicroCT images. To have an idea of what this pressure apparatus or the tri-axial pressure apparatus look like, this is it embedded inside of one CT scanner. And this is another image of the exact same apparatus in a different CT scanner with myself and a colleague to show the scale and how large the device is. So now if we were to consider our rock sample at time 0, where it has not been subjected to any deformation, and then deform it over time and take sequential images of the rock sample, we can see the development of fractures. This data sets can be found in Zhao et al. 2018. And what we intend to do is do a very similar experiment where we monitor, or we take images of a rock sample under different conditions over time and capturing the fracture. So in this presentation, what I'm going to present is an approach of trying to enhance these the fractures for the purpose of analyzing them later. So for the images that I just showed, these images were acquired of a rotary shear experiment where 2 semi-samples were placed on top of one another, and the top semi-sample was basically rotated. And with that rotation, it generated fractures in the bottom semi-sample as shown in this image. Our interest here is going to be considering the fracture surface area. We would like to estimate or improve the estimates of the fracture surface area. Other fracture properties such as volume and aperture and orientation are also of importance, but we are not going to address them in this presentation. So, excuse me for a moment. What I am showing here is the top row, an axial slice that is identical to the bottom row. However, the difference here is the time instance. And in the left column here, compared to the right, in the bottom right image, is basically the reverse image of that. We simply take the image and we take the maximum and subtract the rest of the values from it. We did that because we wanted the fractures here shown as peaks. These transverse profiles are actually, they correspond to a line, to the profile along this green line. And we need to enhance the images for the purpose of detecting fractures, because if we were to consider this very small hair-like fracture, it's going to be very difficult to distinguish that fracture from the background. This is a sandstone sample, or sorry, this is a synthetic material sample, but it has grain. And it is very difficult to detect or try to isolate that fracture, especially if it is very small. And a similar case shows up over here. This fracture actually is created by the merge of two smaller fractures. And although we're able to see the big fracture, the smaller fractures before that is very difficult to isolate from the background. With that in mind, that's why we need to actually enhance the image. To do that, we used a multi-scale Hessian fracture filtering. This method was published in 2013 by Vaughan et al. We applied the published technique on the rotary shear, in the rotary shear experiment data as well. And we also re-implemented the technique to address subvoxel fractures and establish the fundamentals and enhancing fractures in MicroCT images to address other fracture properties in the future, such as fracture aperture and fracture orientation. Well, to do that, we first generated synthetic images. So this is what we call a synthetic fracture image. This is very clean. There's no blur as well. So this is not representative. This is not representative of what image acquired from a MicroCT scanner would look like. But then we added noise to it, and then we blurred it, and we blurred the crispy clean one as well as the noisy one. This image is what would look more representative of what an image that we acquire from a MicroCT scanner. But this basically is an array of 4 images that represent different stages of what an image looks like, and we use that in trying to develop our method. For our method, what we did is we considered a multi-scale, and the multi-scale comes here in the coefficient S in this Gaussian, one-dimensional Gaussian function. And for every S value, we have a different curve. And what we were interested in is we were interested in computing the Hessian for a 2D or 3-dimensional image. Before we get that, if we were to consider a one-dimensional Gaussian, we take a first derivative that looks like that, and then we take a second derivative that has this 2-peak, 1-trough character. And we convolve that this particular kernel with different images with the objective of enhancing the fractures. And we can think of the fractures as local features, and this convolving this kernel with that will enhance them. To elaborate a little bit, if of course a Hessian can only be or a Hessian matrix can only compute it in 2-dimensional and 3-dimensional images, and a Hessian matrix is basically a matrix with the image. So I here is image, with the first component as the x derivative of that image. Excuse me. And to compute these different components, what we basically do is we take an amplitude, in our case it was 1, and then we compute this kernel and convolve it with the image itself. So this is what it would look like in 2 dimensions. This is the Gaussian filter, and this is the second derivative in the x component of the second derivative, which represents the I comma sub x. So we compute all 4 different components of the Hessian in the 2D case, it's going to be a 2x2 matrix. In a 3D case, it's going to be a 3x3 matrix. And after computing all these different components of the Hessian matrix for every voxel, we compute the eigenvalues for every voxel. And after computing the eigenvalues in the three-dimensional case, we would have 3 eigenvalues. Over here, lambda 3 is greater than lambda 1. And then we generate this new function, a sub s, for every scaling factor s. And after we compute this function, we normalize it by the maximum value, and then we binarize it as such, where gamma here is an arbitrary coefficient that we determine based on trial and error. And doing that for multiple s or s coefficients or multiple scales. So this one up here is for s equals to 1. Here is for s equals to 3. And then we can combine the results to generate the cumulative results at the bottom right corner over here. And let's see how the results look like. So this is the original image, which is the blurry image of the synthetic fractures. And then this is applying our implementation, and this is applying the Vorn's implementation to that image. And to see what that looks like, if we were to consider the image that was not blurry, we can actually have a very good resemblance between the enhanced image and the blurry image that does not contain any noise. Excuse me. So now to look at what that actually looks like on the rotary shear experiment data, looking at the exact same axial slice, we can see that fractures in the image that is enhanced can now be isolated from the background. The reason is, as can be shown over here, notice that the background here basically does not contain much noise anymore. We are able to enhance the fractures, and because we binarize the image, we actually almost eliminate the background noise, making it very possible to see the fractures only instead of the fractures and the background noise as shown in the input image over here. So now we can see that this is the non-enhanced image in the top row, and this is the enhanced image. And if we focus only in this small section that is that zooms into this yellow rectangle, we can see that these fractures are much better illuminated. And with that, we can then estimate the surface area of this fracture. And we wanted to estimate the surface area of the fracture because this data set was used in a study where the surface area was published or estimated and published. To estimate the surface area, we used Mavis Lab, which is a medical imaging prototyping software. And we used an isosurface module that was provided that is already programmed into that software to estimate the surface area of the fractures. To estimate the surface area of the fractures, though, we do not estimate exactly the absolute surface area. However, we compare the surface area of a particular image in the future compared to the original undeformed image. And the image we have chosen is the time step number 4, basically, which has an average step distance of approximately 1 millimeter based on Zhao et al. 2020. Our estimate of the fracture surface area, or the surface area due to fracturing, is approximately 762 millimeters squared, and that is better than all of the other published estimates. And we claim here it's better is because it provides a larger surface area estimate than that is closer to the published energy budget estimates due to fracturing. And with that, we conclude that the multi-scale Hessian filtering is very useful in enhancing fractures. It eliminates MicroCT imaging artifacts that could affect the analysis and reduce the noise in the data for our purposes. Our implementation improves the fracture enhancement compared to Vorn et al. And we're also able to use enhanced image to produce a surface area comparable, if not better, than the one published for the same data set. Moving forward, we'd like to use other denoising techniques of MicroCT images before enhancing them. We also would like to consider an anisotropic Gaussian kernel with a range of orientation. This could potentially lead us to extracting orientation information about the fracture, not only surface area and aperture. And we'd like to optimize the filter size for every S value, or the scaling coefficient S, to reduce the computational time. With that, these are the references for this talk, and I thank you all and open the floor for question if the